Today, we will have Kit Chambers introducing plane, trains, and automobiles, applying geophysics to the monitoring of transportation networks using DAS. We have Kit Chambers. He's the Director of Motion Signal Technologies. Kit has been working on problems in seismology and passive seismic for over 20 years. After completing an undergraduate in geology from the University of Bristol, a master's in geophysics from the University of Durham, and a PhD from Oxford, he has worked for the University of Bristol after his postdoctorate, Rock Talk, Imaging, Halliburton, and Nanometrics. Most recently, he has founded Motion Signal Technologies with the aim, amongst other things, of applying his experience from passive seismic to the new and different problems. He is also Vice President of Signal Processing at Focus Sensor Ltd. Today, we're very honored that he has accepted to do this webinar. We think geophysics has many applications for the futures, and today he will introduce to us what this future looks like.
Okay, thank you very much, Annabella. I guess I'll get going. I guess you've all had plenty of time to read the title of these things, and I would say that the spelling of plane is deliberate in the title there, is because actually the train signals that we're going to be looking at are actually relatively simple, although as you'll see, even simple trains can actually get surprisingly complicated surprisingly quickly. So before I begin, let's just try and advance the slides. There we go. I'm going to start off with a little bit of housekeeping. There's going to show you results from several different data sets collected around rail and road environments in this talk. And so the rail data examples are all acquired by Focus Sensors Limited using their Indus DAS system. And the road examples are a little bit more of a mixed bag. There's many that are from the Focus Sensors system, as well as also a publicly available data set that was collected at Brady Hot Springs and is made available through the Geothermal Resources Council. And finally, in the second section of this talk, I'm going to talk about a model or a way of modeling train signals recorded on DAS fibers, and that's the result of a project that was funded by Focus Sensors. So the way I've done this is that all the slides that have Focus Sensors material on them have that Focus Sensors logo down in the corner, just so you're oriented. So given this is an SCG talk, I suspect many people are already aware of what distributed acoustic sensing is, or DAS is. If you're not, then it's essentially a measurement technique that allows you to turn a fiber optic cable into an array of thousands of vibration sensors, and it does that by looking at the backscattered light of that is reflected back up the fiber optic cable. And we'll get into a little bit more of the details on this as we go along, but for the moment, the thing to remember is that this technology is sort of deployed quite a lot throughout the oil and gas sector. Most oil wells have a fiber optic cable in them, but fiber optic cables are everywhere throughout our lives. They take our broadband to our home, they go under our oceans, they go beside our road networks. And the second you realize that, whole new worlds open up for actually what we can and can't monitor, or can monitor with these fiber optic cables. And so in this talk is going to be particularly about transport networks. And so most sort of fiber optic, or most DAS companies sort of show some sort of picture with a city of the future and sort of bright blue lines and things like that. But I think it's actually easy to illustrate this using some children's toys. And so this is my attempt at it, at least here, where we've got our sort of train line that is coming down here. This string that is lying along beside it is a fiber optic cable, which is actually sort of quite a common thing to have in the UK and Europe at least. And the idea is that the vibrations that are caused by this train are going to be picked up by the fiber optic cable. I'm going to use those vibrations in order to tell us information about the train and the condition of the ground around the train. So with that in mind, I've sort of got the following in terms of a sort of vague agenda for the next sort of hour or so. There's going to be a little bit of a sort of prologue type section where I discuss, I'm going to call it typical vehicle monitoring using DAS. And the idea is that's going to set us up for a sort of more atypical example, which is the Brady Hot Springs data set. And I'm going to talk about that in some detail, in particular how we can use array processing in order to detect and analyze vehicles on that, and the properties of the signal that we actually see at Brady Hot Springs, and what that means for surveying sort of roads using DAS in general. And so that'll sort of take us up to halftime, which is we'll then change over to look at rail type data sets, where again I'll sort of talk a little bit about some of the general properties of sort of train signals that we see from these type of environments, but in particular I'll talk a lot about how we can model the train signals that we record on the DAS Finder and some of the outcomes from that modeling. And so the final bit will be where I sort of try and tie all this stuff together by talking about sort of kind of things we can do and things we can't, or at least things that I think we can't with these types of data, and how I think geophysicists can help with analyzing some of the DAS data from transport networks a little bit better. So I think I'm going to start off with typical monitoring scenarios, and so I say typical in quotes up the top of this slide because typical really sort of encompasses a wide variation of settings. But what I mean in this case is where you've got like a road. In this case I've got a freeway, but it doesn't have to be, and usually the cable is sort of, might be buried down the side, or it might be sort of trenched into the road, or something like that. But the idea is it's deployed quite close to the road. It's typically only a couple of meters from the closest lane. And so the plot on the right here is a fairly simple intensity-based plot from a DAS recording. You've got time axis going down the vertical axis and channel number going across the side. So if you like, this is distance down the road on the horizontal axis, and this is time going down here. And so what you're seeing on here with these bright signals is the cars and trucks that are going down this freeway in a sort of fairly short period of time. And you can see there's sort of quite a few different vehicles in there. There's ones with sort of fairly common slopes. The brighter ones tend to be these ones that are sloping right here, and so that is probably the nearer lane. And you've got ones that slope the other way, which indicates it's obviously going the other way along the road. And the sort of typical geometry for a rail type data set is a little bit similar. I put this picture in on the right over here for two reasons. The first is to remind me that there's actually obviously a hazard monitoring application for this type of data. This is taken from a local paper where a couple of years back we had some bad winter storms in the UK, and I think about half the houses either lost or gained a trampoline at some point during them. But the other really good thing that it shows is the cable trough that is running down the side of the railway line. And so that's this sort of concrete structure you might be able to make out in the picture. I'm told you can see my mouse pointer, so hopefully that will outline that for you. And in the other photos I've got some examples of it sort of more open, and the cables are used for signaling purposes, or even some of the telecom providers use them to send signals between cities, and they're pretty much just lying in there for the most part. But again, there's a whole range of different deployment strategies and options for this type of thing. But nonetheless, you can still detect trains using these DAS cables. So again, you've got, this is actually a much longer time section. We've got about 5 hours on our time axis down here, and this is channel number going across the bottom. So if you like, the bottom is distance down the track. And these sort of kind of red lines that are going across here are actually the trains that are going up and down the track in this case. And if you zoom in really close on them, so instead of looking at 5 hours, I'm now looking at just a mere hour of data from this, you start to see that there is actually a slope to these things, which is of course related to the train speed. This is one that's sort of traveling down the track, and at this point there's a place where it stops. There's either a station or a signal or something, and then at the bottom you've actually got lots of sort of some slightly more erratic signals, and that's because I think there's actually some sidings and things like that in this area. But I guess the point I want to get across about the sort of typical monitoring scenario is that even that's actually not that straightforward. The monitoring of these things is highly opportunistic. You're using sort of typically these cables that they're not straight and they're not necessarily fixed in position, so they're not necessarily well coupled to the motion. And importantly, the cable path is not necessarily that well known. We obviously know where it starts and where it ends, but the exact place it takes between those 2 points is not necessarily of concern when the cable was deployed. And so you have to think of clever ways to work this out, because you can't necessarily go and walk along train lines particularly. At least I don't know about the other countries, but in the UK, unauthorized access to a train line is not only extremely dangerous, it's a criminal offense. So you often have to think of cleverer ways in order to actually map out where this cable is going. But nonetheless, it works, and it works really well, all things considered. It's kind of amazing, and it's a sort of testament to the sort of how good some of the DAS interrogator technology is, that we get these clear signals out of this. So if you like, that's the sort of typical case. I'm going to sort of now launch into the meat of this presentation, in particular looking at road monitoring. And that's with a sort of very atypical scenario. And that's this experiment that took place at Brady Hot Springs. So this was, if you're familiar with SEG and the publications on this, you may well be very familiar with this experiment. It was certainly quite high profile at the time. It took place in 2016, and it consisted of many different components. They actually had a borehole DAS, as well as surface DAS and DTS, surface seismometers arrays and pressure sensors and all sorts of things, all with a view of actually monitoring this geothermal reservoir that sits underneath Nevada. And there's been a lot of really good work done on on analyzing these data sets, and I'd encourage you to look at some of the publications on it if you're interested. But for my purposes, or what I'm really interested in here, is two things. First of all the data that is on this is publicly available. If you are sowing, the Geothermal Resources Council has made the raw data sets freely downloadable, so anybody who's so inclined can go along and do this and analyze and reanalyze this data. Then the second point is that they actually had this surface DAS array on here, and so it starts down at the interrogator building and sort of snakes its way a few miles up the upside here, and then before sort of coming back on itself, and then finally finishing in the top right corner over there. So the white numbers here are channel number on here, and the black line is showing the path of the cable. So there's about 8,500 sensors, and it's about an 8,500 meter cable. And what I'm interested in on this is actually the fact that this is running right past a freeway. And so the question is, can we use the signals recorded on this fiber optic cable in order to monitor the traffic going up and down this freeway? And so the short answer is that we can. This is an example waterfall plot, and I apologize, I've plotted these ones sort of transpose style. These are this slide and the next slide are the only two where I've done that. But we've got channel number going down the side here on this one, and time going across the top on here. And so what you see is that signals amplitudes are much higher in the first 4,000 channels, which if you look at our array map are the ones that are closest to that road. And in fact, you can even see sort of a clear sort of move out on some of these signals. They sort of start around, say, channel 3000, and they go at some point and they arrive later down near some channel 0. And that's going to be that is basically a car that's coming from the north of the picture to the south along that that freeway. And there are even a couple going the other way that you can see in this thing. And you can get a sort of sense of motion on these things also from the map plot. So this white line on the map plot is, or the white line on the waterfall is actually the colors for the map. So there's a car sort of about here on at the time that that frame was taken. And so that's all well and good. You can certainly sort of see the car signals pretty clear in here. This is sort of only half an hour of data, but if you note the time axis, this is happening in the middle of the night. That this half hour starts at midnight and it finishes at 12:30. So the question is, well, what happens during the daytime? And the answer is it gets a lot more complicated. We're now seeing much higher amplitudes. The plot is looking a lot more busy on our first 4,000 channels. In fact, we're seeing many cars sort of go backwards and forwards, and the signals are all overlapping each other, and they're all creating this sort of really complicated interference pattern. And you're even seeing a couple of signals which actually stretch right across the array, and these are probably cars that are traveling along this, it's called the frontage road, that runs actually through the middle of the array. But anyway, the majority of the traffic is happening along that highway, unsurprisingly, and unsurprisingly is busier during the daytime. But the thing that this screamed out to sort of me as a geophysicist is that these overlapping patterns easily can be dealt with through array processing. And so with that, we went and developed this technique called velocity stacking. That essentially, this is a little bit like sort of semblance panels that you're probably familiar with if you do exploration geophysics. But the idea is that you pick a particular velocity and you align data based on that velocity. And I should add that's vehicle velocity, not seismic velocity. And you can get and in doing so, you actually separate sort of these much more complicated patterns into a set of relatively simple anomalies. We have, 8 or 9 cars or vehicles that are traveling in this area. Some of them are actually very closely spaced in time, but we can actually resolve that by taking into account the relative move out across the array. And the procedure has a couple of other sort of really nice bonuses to it. Not least, it naturally separates vehicles that are going sort of one way on the road versus the other. So this, the way these are arranged is you've got the slowest velocities sort of in the center on here, and so you're getting progressively faster as you're going north as you go this way, and progressively faster going south as you go to the left of the plot. And these dashed lines are actually the speed limit for Nevada. So this particular vehicle here, which if it is real, then is actually at least at best on the speed limit and quite possibly over it. And that's in this setting at least. Very naughty. So you can of course automate the processing of this type of data, and so the plots on the left over here deal with actually how some thresholding parameters are used in order to actually select out cars. I'm not going to go into those on a lot of detail, but safe to say that you can choose a sort of semi-automated threshold that effectively excludes a lot of your cars. And then, but then what is sort of left out of the, or what comes out at the end of the procedure is actually sort of a fairly nice separation of sort of a vehicle identification and vehicle speed as it comes on there. And so in the 14 hours or so of data that we processed for this, we detected, I don't know, 1,000 plus cars. I can't remember the exact number. And, the main thing that sort of stops us is not actually the processing time in order to do it. It's actually the fact that you've got to choose times to process this data when they weren't doing vibe shots, because the vibe shots just completely max out the array, and you can't see the vehicle signatures as well. So that's a bit about array processing at Brady. I wanted to mention that briefly, but really one of the things I want to discuss about this data set is actually what the waveforms look like, and because they're a bit different. And so the first thing to note about them is that they're highly compressible, and that is something that actually is true for most DAS data in my experience. So this plot on the left here is a waveform recorded from just one of the DAS sensors for a vehicle going past. And the plot on the right is exactly the same thing, but the difference is it's been treated with a compression algorithm that knocks the data volume down, in this case by about 85%, although we've got we've had some developments on that end, and it can probably get closer to 99% now. And so this is important, if nothing else, because it decreases your data transmissions and cloud storage costs if you can knock a factor of between 10 and 100 off the data rates that's coming out of these systems. And the real thing that, the other thing that I wanted to notice from this plot is that actually these pulses are very emergent. It's sort of this it takes about sort of 15 seconds, and it's this sort of broad fuzzy type signature, and it's typically sort of 10 hertz sort of to 20 hertz sort of band on this. So
could you elaborate a little bit more on the data compression? What do you mean about compression?
What do I mean about compression? So firstly, there's details in the TLE paper of the compression algorithm. In terms of actually what I mean about it is the number of bits that are required in order to store this particular waveform. So the one on the right, if you store them as sort of standard 4-byte floats, or even sort of 2-byte differences, you can treat them with the compression algorithm, which is based on a wavelet decomposition. And by doing so, it actually, I should point out, it's a lossy compression. You don't get anything for free on this, but it does at least preserve most of the signal. In fact, if you look at the time frequency up the top here, it's sort of keeping sort of main bits which are the signal, and actually the bits that it gets rid of are typically the sort of noisy rubbish that happens around the side. Is that good enough? Okay, shall I continue?
Yes, please.
No problem. So where was? Oh yeah. So bearing in mind these waveforms are sort of these very emergent, fuzzy pulses, the typical signals that we see from traffic is not really like that. This is another example from a fiber that is deployed alongside a freeway, and in this case, you know, this is an example recording from it. And these are different vehicles going past. You know, we see these very low frequency, very simple, sort of very nice up-down pulses, and in fact, often the up-down parts are actually related to different wheel sets on the vehicles, and they're typically very coherent. And that's nothing like what we're actually seeing at Brady. Brady, we're seeing these, we don't see this sort of nice, simple shape. I know these plots are on slightly different scales, but they're not that different. You're seeing, instead of you know, this nice frequency, this nice sort of low frequency stuff, you're seeing a sort of more emergent style of pulse. And the explanation for that, I think, is actually kind of interesting. And it comes from considering the frequency content, or when you look at typical road traffic signals. So in this example, I've got the same data set from a road traffic DAS array. You've got, again, channel number down the bottom and time going down the vertical axis. And on the left-hand side, there is we've got it run with a low-pass filter, sort of, I can't remember the exact numbers, but it's of the order of 3 to 5 hertz. And on the right is a high-pass filter, again, order of 3 to 5 hertz. And so with our low-pass waveforms, you know, what we see is something that's referred to in the literature as a quasi-static response. And Siwan's paper from Leading Edge last year actually shows a pretty good has a pretty good description of this, and you can actually model it analytically, or there are analytical expressions for this signal. And the details of this formula are sort of not critical to our purposes here, with the exception of this part in the brackets. And so one of the things that you might note, if you're particularly sharp, of particularly sharp vision in the brackets, is that you can take a 1 over R factor out of those, out of that term, and that 1 over that R is actually a distance is the distance from the source to the sensor. And so 1 over R terms always look very suspicious to geophysicists, and they generally scream body waves at us. It means that it's actually caused by a wave that's expanding through the material. And whereas if you look at our high pass response, one of the things that we see is that it actually propagates much further away, which is counterintuitive in itself. You'd expect the high pass components to be attenuated more. But also it propagates more or less linearly with distance. And that sort of thing screams surface waves at you. And in fact, the velocity of these things are usually pretty consistent with Rayleigh waves traveling along the free surface of the material. And so surface waves don't decay with a 1 over R term, they decay with a 1 over square root R term. So they generally attenuate much slower as you move further away from the source. So what are we seeing at Brady? Well, at Brady, we're much further from the road than we are in what's called the typical setting. And typically, in the typical case, you've got the fiber maybe within a couple of meters of the closest lane of what you're monitoring. It's rarely ever much more than 10 or 20 meters. In the case of Brady, our sensors are actually our closest sensor is about 50 meters away, and the typical sensor distance is more like 100 to 200 meters away. So there's an order of magnitude difference in the distance of these sensors to the road compared to what we're usually seeing. So that quasi-static response, which remember it attenuates much more quickly because it's a 1 over r term instead of a 1 over square root r term, is actually just reduced out too much by the distance. And so what's left after that is the surface wave response that we're seeing at Brady, or at least that's the current belief on these things. And so now that we know a little bit about what we're looking at, there's one final sort of thing that I wanted to point out in this Brady dataset, and that's actually looking at some of these time frequency plots in a little bit more detail. So again, this is our signal coming along, the time for our signal coming along the horizontal axis, and frequency content coming along the vertical. And one of the things that you notice is that actually as the vehicle sort of signal arrives, there's this shift from high frequency to low frequency as you go. And my initial thought was that this was actually surface wave dispersion, but it's actually the opposite from what you'd expect from surface wave dispersion. Surface wave dispersion should actually result in lower frequency components arriving first, so it's the wrong way round. Instead, I think what is happening is actually a Doppler effect. And hopefully this sort of crazy little animated GIF is coming through on your screen, but essentially because we've got a moving source in our causing our signal. So as the source travels towards us, if there's a sort of relatively constant frequency, then that frequency is shifted up, and as it passes our source and then travels away, that frequency is then shifted down. And so that's what these black lines are on this plot. I've done a sort of quick back of the hand calculation for perturbations to 11 hertz and 21 hertz frequencies for a particular sort of source velocity and medium speed. And it could do with some tightening up, but it's at least ballpark. It's sort of, it seems to be fitting reasonably on that sort of on this sort of scale. And where I think this is potentially really powerful is that it provides a per sensor basis way of actually judging vehicle speed, where instead of actually as a potential sort of augmentation to some of those array-based methods. So
there's a question about if you see any effects from the road surface differences.
Do I see any effect on the road surface difference? Not a lot in this case, but that doesn't mean it's not there. You're looking sort of quite a long way away from the road surface on here. So, but I would say the analysis that sort of has gone on with this data set so far is, you know, it is relatively basic. There's a lot more that could be done, and that might be one thing that's worth looking at.
And another question is, what type of sampling do you typically use for traffic monitoring? And with respect to when you compress the signal, do you compress it before processing?
Depending on what, it depends. We often do compress it before processing, or at least in this case I did, because it knocked my cloud costs down in order to do it. But you don't necessarily have to. In terms of sort of sampling that is used, typical sort of DAS sampling rates are sort of a meter or so down the fiber, with sort of gauge lengths that are sort of, 5 to 10 meters. And time samplings, we're looking at actually sort of quite low frequencies on these data. So these systems are all capable of recording very high sample rates of the order of, 1,000 samples a second. So, but whether you actually analyze the data with that higher sample rate, that's up to you. It just depends on whether you want to downsample it or not. Certainly in this case, I think I downsampled it to about 250 samples a second, just to sort of get through a bit quicker.
One more question is how
yeah, sure.
the sensitivity of DAS impact those monitoring studies?
The short answer is it does. And you can actually even see it on some of the array maps. There's a clear directional sensitivity, and particularly with that Brady array where it's actually zigzagging through the desert there. One of the things that we did with the velocity stacking is take an envelope function to start with, and the idea part of that was actually to get around some of the issues with the directional sensitivity, because if you had sort of sensors facing different ways, then you could in principle actually have the same signal that's reversed in polarity or something like that. And this was going for sort of a quick first pass approach, so an envelope function got rid of a lot of that for us. I've basically done sort of more or less sort of finished on the Brady section of the data set. This is kind of my half-time summary that I've put together here, and literally the points that I was, the takeaway points from this section of the talk is that yes, we can use these sort of array processing tools in order to detect vehicles, and probably do a lot more with these data sets. But also it's important to consider the actual, what's the signal that we're actually looking at. And in this case, we're looking at this, we're not looking at this quasi-static response, we're looking at the Rayleigh waves arrivals. And where that's interesting is that it means that we can actually monitor these assets from much further away than is permitted by seeing. If you required seeing that quasi-static response in order to do the monitoring, then you have to have that. Then you need that fiber much closer to the particular asset. And I think the Doppler shift could, for determining vehicle speed, could also show some promise. So I can move on to Rail if there's but are there any quick questions, Annabella?
No more questions for now.
Okay, that's cool. Everybody is just amazed at my explanations, quite clearly. Right, so rail monitoring. And
sorry, Kit. Leo Eisner has
hey, Leo.
his hand. So let me promote him really quick. Let me allow him to talk. Leo, can you talk?
Yes, I think I can. Hi, very nice presentation, thanks. I was just wondering what's the advantage of wavelet transform over, let's say, resampling of the data?
Sorry, what over resampling of the data?
Resampling, downsampling to, let's say, lower rate versus wavelet transform or compression in
the advantage is you can do both. Why don't you compress it out? Why don't you compress it and downsample it? Then you can have a really small data volume that transfers really quickly.
Yeah, but by wavelet transform, you really already implement some model. You basically show that you remove some of the noise, but maybe that was a signal too.
Yeah, and that's something that needs to be taken with care. Certainly, I've tested that on a number of data sets, and it sort of produces pretty faithful results. But I think sort of these typical DAS data sets are pretty cumbersome to deal with, and so having a way of getting that data, even in downsampled format, out of the field is a pretty useful thing to have on that front. And there's nothing stopping you always keeping full resolution for later use if that's something that you're concerned about.
I was just wondering why do you think, and do you do the wavelet transform only in time domain or also in the space?
It's pretty much in time domain on that case.
Okay, thank you.
All right. So changing tracks to rail. Sorry about the pun. I guess it probably is worth discussing some of the general properties of train signals before we begin. And so these two pictures at the bottom are to remind me that actually a lot of the examples that I'm going to show and a lot of the examples that I'm going to talk about are European, where of course we have passenger trains. I know you have passenger trains in the States as well, but here we have a lot of passenger trains. And they actually also come in all shapes and sizes. And in particular, the sorts of signals you see from them are surprisingly consistent despite that. So this is an example of a data set on the data set collected on a DAS fiber. In this particular case, it was a blown fiber, I believe, which I'm told is a difficult configuration. And we had a road that was going along one side of the fiber, and then you had a train going along the other. And so what you see is this sort of very slow-moving truck that is going along the road, and then a much faster-moving train that is going along the railway track as both past the same set of sensors. And one of the things you notice about the train straight away is that obviously it's your slope indicates speed, just like for the cars, but you also have these stripes that are pretty typical on trains. And we've been calling these zebras because, well, they're stripy. And they're typically very clean type signals, and often the peaks and troughs in these are often indicative of the individual wheel sets on the train. And so this is another example train signal. It's slightly more data in this case. It's about 2 minutes or so long, and you're looking at about 7,000 channels. So this is it's traveling along 7 kilometers of fiber or so, and you can see this sort of fairly coherent zebras as you go along in certain places, at least on the signal. But the other thing I really wanted to point out on this picture is that you actually have these flat spots in the signal. And so obviously these are not places where the train has achieved infinite velocity or encountered some sort of wormhole in space that has teleported it. What has happened in these cases is there's actually a coil in the fiber. The fiber is not necessarily all lying perfectly in a straight line. And so although the channel count is increasing in these areas, the geographical location is not changing. So it appears as having an infinite velocity. So any processing that you have to do with these things is going to have to take that into account. And what I want to do with the next few slides is actually talk a little bit about how we might model these train signals. And it's quite a simple model. We're going to build it up from first principles, and see where it takes us in the scheme of things. So the idea is quite easy. You've got a fiber optic cable that is deployed alongside your track, and the principle is that trains are really heavy. So the main force in the system is actually the weight of the train, which presses down, and somehow that creates seismic energy, which is going to be picked up by this DAS cable. And So we can start off with what is a sort of very typical response, a very typical problem for geophysicists, and that is, well, what's the response of a point force on a half space? And so this is some example synthetics that I computed here. You've got some time going down here and distance from the point force position going along the x-axis, and you can do all sorts of different components in this case, and even in this case we've got actually some attenuation and dispersion in there because it's a multiple layer system. And we can, the only thing that is maybe a little different in this case is that we have to do we have to take account of the fact that a DAS is a finite strain sensor, so you have to take into account of the gauge length between your sensors when you're constructing these things, but none of that's impossible. We can sort of go ahead and do that. Things get a little bit more complicated when you consider that a train is not a point force. They in fact have wheels, and that wheel actually sits on top of a rail, and so the force is transmitted, or it actually bends the rail and then transmits the force through the sleepers into the track. And how the way in which this rail bends is modeled by something called a rail deflection function, and so that has an effective length associated with it. And this is something that's actually of interest to the engineers because a short effective length means that it's a sort of weaker track because the bending is going to be more localized, whereas a larger effective length means that your anomaly is spread out a little bit more and you've got a much stronger track. But you know, we can go and incorporate that into the analysis. But of course, trains don't just have one wheel, they have many. And in fact, they're actually organized into different sets. You actually obviously have multiple wheels on each axle, and you have different sets of wheels. They're called bogies. And so you have a different spacings between your wheels. You have a wheel spacing, bogie spacing, and then you also have a carriage spacing, which comes in important in a second. And you have to position all these wheels in order to actually create the signal model. And so you can sort of put all that stuff together and you can create what I've been calling a stationary response function. So this is a bit of an abstract thing, but the way to think of it is if you had a section of railway track with a fiber optic cable lying on side it, and the train just suddenly appeared out of thin air on that track, this is the response that you would see on the DAS fiber. Or another way of thinking about it is if you took your track and you hit it with a train-shaped hammer, then you would see, these are the sorts of signals that you'd see. And you'd see essentially point sources from each of the wheels that modulated by things like sleeper positions and the deflection function, and you'd see the pattern, and they would interfere and create this sort of complicated sort of checkerboard pattern in here. But of course, trains are not stationary. Trains are moving, and so you actually, what you have to do is you have to take that stationary response function and treat it as a running sum along your track. And so I've got two examples on the left here of just exactly the same train, but just running at different speeds. Unsurprisingly, you've got the velocity changes. If you've got a slower velocity, then you end up with a much steeper diffing curve on these things. And you can already see that we've got these sort of zebra patterns, which is what we saw in the data earlier. But I think one of the things that sort of, you realize the power of some of these models when you actually start considering what happens when you take Fourier transforms along these things. So the next slide I've got is a Fourier transform of a signal going down In fact, I think it's the central signal from one of these cases. And so it results in sort of these frequency spectrums. So we've got a frequency along the bottom axis and amplitude or normalized amplitude going up the y-axis. And the red and the black curves are the spectrum that you see for sort of two different trains traveling at the same speed, but they've got different compositions. And as a geophysicist, the first thing you notice about this is that it's very low frequency dominated, and it's very band limited. These are not like the source spectra that we're used to looking at in passive seismic or even active seismic scenarios. They're sort of very bumpy, I guess is for want of a better word. They've got a lot of notches and distinct signal peaks. And often those signal peaks are actually good indicators of the actual train composition. And one peak in particular that is usually dominant, and this is called the carriage frequency on this. And so the reason that's called the carriage frequency is because that frequency spike is nearly always the train velocity divided by the average carriage length. And so this is an example I've got showing it on the sort of middle and right over here, where you've got a sort of, again, you've got dash channel going along the bottom and time going along the vertical axis. And so we've got our fairly clear train signal. And then on the right hand side, I've got the same traces, but as a frequency response. So instead of time, I've got frequency going down here. And so this is our carriage frequency coming in at about 1 hertz along here. But what you notice is that actually as you go past about sensor 1900, that frequency shifts up. And there's essentially sort of two ways that can happen. Either the carriage has gotten shorter, which seems a little unlikely, but the more likely scenario is that the train sped up in that area. So this is actually, this carriage frequency is actually a very sensitive indicator of the train speed, because you wouldn't necessarily see in your raw data sort of a subtle change in the speed like that. In terms of other outcomes from the modeling, I think one of the interesting things you can do is look at the effects of different train compositions, and in particular the different spacings on this. So I've got 3 examples of spectra or modeled spectra on this slide, and the red line is actually an observed spectra. So the red line actually has a sort of fairly clear carriage frequency, which you might be able to make up, as well as sort of various lumps and bumps as it goes along. And the sort of better matching spectra are probably the Electrostar or the Pendolino train models. And the reason that is because these different wheel spacings on these different models create different changes in these spectral compositions. So with that in the bag, there's sort of the final thing that I wanted to sort of go into on or the modeling outcome I wanted to go to from the train spectra is the influence of train speed, if you like, and just because it makes for an interesting thought experiment, if nothing else. So I've taken the same train and I've run it at 3 different speeds on this, and this is a time series recording, so you've got time across the bottom and sort of strain or going along the y-axis. And obviously when it's sort of going slowly, you see a much broader pulse where you can see the sort of clear wheel sets in the response, and as it gets faster, that response gets sort of shorter and starts to bunch up until you're actually starting to get very fast. So 100 meters per second is sort of, you know, bullet train type territory, where we're actually seeing sort of extremely high amplitude features, and in fact actually the sampling rate of the synthetics is probably not sufficient to represent this. And the reason is because actually I set the medium to be a very low wave speed. Well, it's 100 meters per second in this case for a Rayleigh wave speed. And so what's actually going on in this case is that you actually have what's called it's not a sonic boom, it's a seismic boom. So the train is actually starting to travel faster than the waves that it is generating. And so you end up with this sort of Mach cone type effect. And this isn't actually that abstract an example. Amazingly, people have actually observed this because Rayleigh wave velocities, particularly in sort of shallow surface sediments that are poorly consolidated, can actually be very low. In fact, they can be lower than much lower than 100 meters per second. And so there was actually a case in Sweden in the 90s where this thing was actually seen on a high-speed railway line. So what they do now when they build the bullet trains in sort of Asia and Europe is they compact down the foundations that the train's going to go on, and the specific, well, there's a number of reasons for that, but a big part of them is so that actually by packing down those foundations, they increase the Rayleigh wave velocity, and so they actually stop this type of seismic boom from happening. And so that's kind of the end of the modeling section of the talk. There's one last sort of little thing that I was going to throw in as a sort of observation on this type of data, and that's actually looking at some of the very low frequency components of the data. Because one of the great things about DAS is that it does actually have the potential to give us some very low frequency observations. So in this case, we're actually looking at sort of the frequencies that are typically much lower than the carriage frequency on these data. And what I've done is I've plotted, it's actually the same DAS fiber, but we've plotted amplitudes sort of observed on those frequencies at on different trains at 2 years apart on the same map. And so what you actually start to see is that on one, we actually have a much higher anomaly associated with this. And in fact, actually, we did this, this was done a couple of times, and you see they had between a train in 2018 and 2020, there was a big change in those low frequency amplitudes. And then again between 2020, which is the slide on the right here, and 2021, the actual amplitude reduced again. And that's actually because what they did, my understanding is that they actually went through and retamped the ballast in this area. So there was actually some track maintenance that was performed. So this, so what this low frequency signal is telling you is about the condition and the stability of the track. So this is another section where we've seen these sort of high amplitude, low frequency anomalies. And this is actually a photo of the section of the track. And so this, I believe, is the cable trough where it was deployed going down the side here. And I think it's fairly clear that this was not sort of built with this sort of rather crooked line on here. It was almost certainly built with a straight line going down the side. And what's happened is there's actually some slope stability and some ground movement that is happening along here. And this is actually something that we're picking up in these really low frequency signals. So I think I think I've sort of gone on long enough. I'm going to try and sort of draw this to sort of some type of conclusion for everyone. I think the way to do that is to sort of talk about sort of things that I think are sort of, well, I've said it as things that we can do and things that we can't, but I think it's actually more that things that are sort of well on the way and things that are sort of still arriving might be a better way to phrase it. And that's it. And that's it. Applying sort of trace and array-based processing techniques in order to extract these vehicles is sort of definitely possible. And as geophysicists, that's been our bread and butter for 50 years now. And I think doing some simple modeling of the recorded signals is definitely sort of produce some illuminating results with these things. But there's plenty that I think we could get better at. And I think there's a role for the geophysical community to play in that fashion. So I think also the influence of the subsurface is it's a bit of a no-brainer. I think, as geophysicists, we should be pretty good at that. But I think there's also some work to be done in sort of understanding these signals as you're very close to the source, and in particular accounting for the fact that these are moving sources. Most of the geophysical tools that we have are based around the monitoring distance being, very far from the source, at least compared to the source dimension, and that's just not applicable in these settings. And so with that in mind, I think there's sort of something that there's particularly some burning questions regarding the relationships between some of these sort of near field sort of quasi-static type effects and these further field Rayleigh wave type effects. And sort of to remind me of that, I apologize for finishing with an equation. Aki and Richards actually has some analytical formulae for how these how near field and far field terms separate for standard seismic problems. And at least, and as far as I'm aware, or at least I haven't found sort of anything that really sort of helps in a similar analytical sense with this problem of moving sources on a on a half space at least. And so the sort of parting words I have on this are that there's a lot of information in these data sets, and they can tell us a lot about what's going on in transport assets as well as the condition of infrastructure. And a lot of our seismic tools are applicable in these cases, but they're not necessarily all applicable directly out of the box. In some cases, we need to adapt our tools and our thinking for dealing with these types of data. So I'm going to finish up. I think I'd like to thank, if you've listened this far, then thank you very much. I know that October 2021 had a lot of geophysical meetings in it, so it means a lot to me that you've dialed into this particular talk. And I'll also like to acknowledge Focus Sensors and for their for various data examples, as well as the Poritomo team who collected that Brady Hot Springs data set. And I think that's me about done.
Thank you, Keith. We have a couple questions on the Q&A box. One, what's really low in terms of frequency, sub-hertz?
Yes, sub-hertz, definitely.
Okay, second question is, what is your main purpose on this study? Monitoring and maintenance of rail traffic?
Sorry, can I get the question again?
What is your main purpose on this study? Is it monitoring and maintenance of the rail or the traffic?
I think all of the above. I think sort of being able to monitor where the rail traffic in real time definitely has applications in several settings, and I think also being able to look at the state of infrastructure in more detail has a lot of applications, and there's more work to be done in both of those areas.
Okay, Leo has another question. What kind of near-surface wave velocities do you observe? Do you observe sound waves? How much dispersion can you observe?
Dispersion, that's a tricky one. Okay, so the typical velocities that we see are pretty variable, particularly between the different settings. So at the Brady Hot Springs area, I believe the near surface velocities are actually very fast because you're sort of dealing with this sort of hard desert rock. But in some of the rail environments, you're dealing with much lower velocities because you've often got sort of much looser sediment on top of these things. And putting an exact figure on those is a bit tough, so I'm going to skirt that question, Leo. In terms of a dispersion effects, again, that's a tough one, because it's not clear to me how having a moving source also impacts the dispersion curves that you see. Now, I know there has been some good work by I think it's the is it the Stanford group on looking at dispersion from cars, but having the fact that you've got a moving source which automatically shifts the frequencies anyway, you need to account from that before you actually deal with any dispersion effects. And even then, if you're looking at very close to the source, it's not necessarily a nice surface wave that you're seeing. You're seeing those that surface wave mixed in with that quasi-static response.
All right. It's time. I don't have any more questions on the chat. Can I give it another minute, see if somebody wants to raise their hand? Okay, here we go. I got Pawelek. Modeling is definitely helpful in understanding new sources and their propagation patterns. How can we use these sources to infer subsurface properties? It was not clear to me what was the low frequency attribute displayed on the map.
Okay, so the low frequency the details of that low frequency attribute are protected, so I'm not going to be drawn too much on the details of that. I'm very sorry, but I think in terms of the modeling that can tell us what can that can tell us about the subsurface, I think the key there is that you've got to actually understand your source before you can even look to remove it, or even know what your source or what your signals are telling you about the subsurface. Because the thing that we do know is that these signals are created by moving vehicles, and we know that that information is propagating through the subsurface to our sensors. So if we can actually handle our the information from our vehicles correctly, then we can glean a lot more about the subsurface. And there certainly are other examples where, for instance, we can create models for the same vehicle using sort of different subsurfaces, which tell us, different things about the properties of the signals.
Kit, this is Dave Diller. Can you hear me? I'm a
yeah
panelist. Thank you very much. It's a really interesting talk. So I know this is slightly off topic, but I have to think a lot of people are kind of wondering what I am wondering, which is, could you comment just a bit on the existing and potential business opportunities for this kind of work?
Okay, well, I'm not a business guy, so I can't put numbers on that for you. I apologize on that front, but the thing I would say is, you've only a quick Google search will tell you that fiber is everywhere. The fibers run, throughout our cities. They run down beside they run down beside our train lines. They run even under our oceans, and not all of those fibers are in use at a particular time. There's quite a lot of dark fiber that goes along there. So then it becomes a question of, well, there's plenty of opportunity to collect data out there. It's a question of finding the right, I guess, or the useful question that someone wants to answer with that data, and there's certainly no shortage of those in dark fiber, but the actual specifics of of how the numbers add up is not necessarily something that I can give off the top of my head.
Okay, fair enough. Yeah, I do understand. I do, one thing that actually kind of concerns me. So what led us to this is our interest in diversifying what geophysicists do. We all understand where the money comes from in oil and gas. But in this case, it would presumably be government entities primarily, or maybe large utilities, railroads, et cetera, that actually be willing to pay for the work, which might make it rather slow moving.
Oh, definitely. I think it's fair to say that one of the tricks, or the tricks with this sort of data, is actually just getting the data in the first place. And there's a lot of work that goes into that, and a lot of work that focus sensors have done that goes into that. It sort of clearly varies from country to country. So, like you say, in some places there might be public utilities. In some places they may actually be private companies that are interested in sort of, I don't know, say knowing about threat detection around their fiber or something like that. And I think that's one of the challenges for the industry. We've sort of got the knowledge, but it's sort of getting that getting that knowledge to the right stakeholders is perhaps more difficult than doing the science.
Okay, Leo has another question. I'm going to allow him to talk. Leo, if you can unmute.
Yeah. Just this is kind of related to what Dave was asking. Like, what's the value of knowing the velocity of vehicle which is coming around in the age when you have camera on the side of the road which measures the velocity and possibly the license plate of the car? So you were showing that we can do it. That's cool, but what do you see as a value? Or another way, maybe the value is that you have these optical cables everywhere. So how many repeaters do you need in the city to have this measurement everywhere? Because that might be cheaper than the camera, or I don't know. I would like to hear you.
Yeah. Again, there's strengths and weaknesses, and agreed. So with the DAS systems, you can obviously monitor much bigger areas, or potentially much bigger areas. Although some of these line of sight cameras are pretty good. One of the big advantages or one of the things that I like about it is that it's actually a lot less intrusive as a technology. It has it's very hard to, we're a long way off being able to work out someone's identity based on the signals that are recorded on a DAS fiber. And so that's certainly a plus in many settings. And the other really big advantage for it as well, which is not necessarily realized by just sort of, picking vehicles, is actually comes from doing a lot more detailed analysis of the data, because the actual data that you're receiving on that DAS fiber, that's not just the vehicle, it's actually propagated through the subsurface. So there is information on the subsurface, and, cameras can sort of see the top of the road, but they don't necessarily see the underneath of it. So there's strengths and weaknesses in there. I'm probably not the best person to comment on sort of social issues surrounding these sorts of things, but there is a place for it.
And can you comment like how many vehicles you are able to, let's say, resolve in the time? Like, can you see when there are two cars driving by each other, or?
Yeah, for the most part. So it depends a little bit on the setup, but if you've got if you have sort of closely spaced vehicles, then in principle, you can distinguish those depending on the particular setup. The Brady dataset's maybe not a very good example of that, because you're sort of further from the road and you've got to do these envelope functions and things like that. So it's you may be looking at you can distinguish sort of vehicles with different velocities, but you're maybe sort of, in order to do that, you're reducing your spatial resolution. But with more typical geometries where you're a bit closer, you can start to do you can start dividing your fiber up into much shorter segments. And so you can actually start to track vehicles much more effectively. You can tell a lot more about what's going on.
Thanks.
All right, at this time, I don't see any more questions. I want to thank everyone. Oh, yes, there's one. Hi, Kit, thanks for the presentation. From Das, can you say what lane the car goes on? Can you say what the lane, can you say in what lane the car goes on the, let's say, 4-lane road?
Okay. Well, you can definitely tell which way it's going. So if you assume that it's driving on the correct side of the road, then you can start to then you can start to then you can ascribe it to a particular lane. As for sort of, you know, a finer sort of resolution on distance on these things, that's something that is definitely of interest and sort of but it's something that is sort of not quite there yet. But I think there's sort of some really interesting data sets out there which are sort of excellent for looking at that, because there will be a difference between the signals you get from sort of moving sources at different distance. But the problem's sort of quite hard because the source is moving, and it's still moving by a much larger distance than, or it's still moving much more laterally than it is in terms of offset.
Okay, second question. In the traffic monitoring section, you mentioned a TLE paper. What
Yes.
of the paper? And so I guess what volume of the TLE?
You know what? Drop me an email. I'll send you a print of it. It's probably the easiest way. So I referred to, so I wrote one which was in November last year, so November 2020. I forget what volume. And the other one that I referred to is C1's paper, which I believe was October 2020. But yeah, if people just want to drop me an email, my email's on this slide, and I'll point you in the right direction.
All right, at this point now, I don't see any more questions. So we want to thank you, Keith, for this presentation and letting us know how to use SAS technology and geophysical applications for traffic and analysis of signal. And we will have a monthly series, so be on the lookout for our next webinar in the next 4 weeks. And again, Kit, thank you very much, and thank you everyone for attending. Have a good day.
Thanks, everyone.